Okay, so we're going to take a look at electrical conductivity in saltwater solutions. Well, pure water is not a conductor. In fact, it's a pretty good insulator. But if ions are present, they can move towards the electrodes, and this flow of charge is the definition of electrical current. Ions can be put into solution in a couple of different ways. If the voltage is above a certain threshold, electrolysis occurs, and the water is split into hydrogen and oxygen gas, and some intermediate reaction products include hydronium ions and hydroxide ions, and that gives rise to some conductivity. Ions can also be introduced by direct addition of salts into the water. These salts dissociate into anions and cations. Conduction is mostly an AC phenomenon. If the voltage source is DC, the ions will tend to accumulate near the electrodes and conductivity will quickly drop. But if you use an AC signal, then the AC periodically reverses direction, and that prevents ion accumulation at the electrodes, and you can get some significant conduction. I've run a few simple experiments to explore AC conductivity with some common salts. I'm using a low test voltage to stay out of the hydrolysis region, and I also want to take a look at any frequency dependence. So before I get into the data part of this, I just want to start off with a quick demo using a low voltage light bulb and power supply. Start with some distilled water and add some common table salt to it and just show the effect. So there's a number of factors that influence conductivity then, voltage, type of solute, concentration obviously, temperature. I didn't control but I did monitor it, and it's at ambient temperature, which is about 17 C, and I'm especially interested in the effects of AC frequency. So here's my test setup. A small beaker holds the solution and a pair of graphite electrodes. A signal generator provides a voltage source with a frequency adjustable from a fraction of a hertz to 10 megahertz. The input signal is monitored with an oscilloscope, and the radio frequency AC signal across a small resistor is fed to an RF probe, and the resulting DC voltage is then fed to a voltmeter. So my setup then, I've got some starting chemicals of 99.9% pure sodium chloride and potassium chloride, distilled water, and a test cell, which is just a small plastic beaker, and a pair of graphite electrodes, and those are salvaged from a D-cell battery. And then on the workbench, my signal generator and monitoring oscilloscope, and a high impedance voltmeter to take my readings. So I took some current measurements with saturated sodium chloride solution that's about 6 molar while I varied the signal generator frequency. So on this plot here, the vertical axis is current through the solutions. That's about 4 milliamps full scale on this chart. That's plotted as a function of the signal generator frequency, and that ranges from 1/10 of a hertz at the low end to 10 megahertz. At very low frequencies, which is approaching DC, you can see you have little to no conductivity, but the current increases rapidly with frequency and reaches a plateau at about 1 kilohertz, and then stays almost flat until the upper limit of the frequency generator, which is 10 megahertz. So it's pretty much constant over 4 orders of magnitude. Here's a look at sodium chloride at several different concentrations. The lower graph is for 0.01 molar solution. The middle graph is 0.1 molar, and the top curve is 1 molar. Conductivity increases with solute concentration, as you'd expect with more ions in solution, but the concentration dependence is very nonlinear. Increasing the solute content from 0.01 to 0.1 molar, a factor of 10, gives you about a factor of 2 in conductance. And when you go from 0.1 molar to 1 molar, the conductance is only increased by maybe 15 or 20%. So things definitely level off at the higher concentrations. Next, I took a look at a different salt. This is potassium chloride. And I tested two concentrations, 0.01 molar and 0.1 molar, over that same frequency range. The behavior is very similar to what I saw with sodium chloride, and where you've got a tenfold increase in molarity results in a current increase in a very nonlinear way. This is a side-by-side comparison between sodium chloride and potassium chloride at the same concentration of 0.01 molar. Potassium chloride solution has higher conductivity than sodium chloride at any given concentration and frequency. And this makes sense, as potassium ions are known to be more mobile than sodium ions in aqueous solutions. Now, residual solutes can have a strong effect on conduction. Tap water has a high concentration of natural dissolved minerals and also some intentionally added chlorine and fluorine. Distilled water has less of these, but it still isn't completely pure. This leads to my final graph. The top curve here is a repeat of the data for saturated sodium chloride, and for comparison I've also shown the corresponding curve for tap water. It's got a fair amount of conductivity because the residual minerals present. Interestingly, it doesn't start to conduct until the frequency is at least 1,000 hertz. And finally, I plotted some data for distilled water. Conductivity here is low, but it's still measurable, and it doesn't occur until the frequency reaches about a megahertz or so. So this highlights an important point about water purity, because water is never truly pure, and the purer it is, the more quickly it becomes contaminated. There's a thermodynamic driving force for purified water to combine with other substances, such as atmospheric gases. In my test, I discovered that an open beaker of distilled water will give higher conductivity after sitting overnight. And this is because of absorption of atmospheric carbon dioxide, which decomposes to carbonic acid and introduces ions to the liquid.